This is our Marshmallow project. These are the people who did the project. And by the way, Cole is not in first period, he's in third period. This is where it explains who did what, and hopefully this is an accurate enough representation. Here's the building process.
Okay, so we have a PVC pipe right here, and this is for the catapult, and these are the corners to keep the pieces together, and these are TVs. To also this is used to hold the marshmallow when we pull it back, and this is a whole bunch of holes in this so we can have the rubber bands in it, and these are the rubber bands that we are pulling back the marshmallow with. Alright, so Cole and I just built the base for the catapult, so it looks like this. It's just made of PVC pipe, and next we're going to take the rubber bands and we're going to just make the launcher, and then we're going to have the thing to hold it to release the marshmallow. So we'll have a time lapse for that. Alright. Okay, we just made the marshmallow launcher like when you pull it back, so it'll be connected to another pair of rubber bands. So it's like that. Okay, so we just made this part, and it's going to be what's going to hold the marshmallow. So we're going to put the marshmallow in here, pull it back, and it's going to be able to shoot. So we're going to be doing some test trials, and then we're going to be finding our data. Alright. Okay, so we encountered an issue when we were testing our marshmallow launcher right before we actually found the data, and that was when we actually shoot the marshmallow. The sides would fall down, so they weren't actually shooting from the same spot, and we thought that would change our data. So we decided that we would tie the rubber bands over these rubber bands so that they would stay in the same place. So that after we shoot this one, it stays in the same place as opposed to this one, which falls after we shoot it. So we're going to put that on for both of these sides, and then we'll be able to find our data.
This is our video analysis with Longer Pro. As you can see, I've already done the actual video analysis because it took quite some time, and I didn't want to waste extra time. So what I have here is I set an order to where the marshmallow was going to be launched, its initial launch area, and then I set a scale from where the marshmallow was being launched to this person's foot, which was pretty much where it finished. And I labeled that as about 5 feet. And I made a position versus time graph for the horizontal axis, and then a velocity versus time graph for the vertical axis. And for the data analysis, Brian messed up on the equations a little bit. He said them in a way that would be a little unclear, so I'll just clarify them. Position in meters equals negative 8.687 meters per second times time minus 0.0599 meters. And for velocity, velocity in meters per second equals negative 9.847 meters per second squared times time plus 3.677 meters per second.
So here is our position versus time graph. This shows us the most part of the background. One starts at exact ground level. And since this graph indicates the horizontal motion, the line is linear. For this reason, there will be a constant velocity for the horizontal velocity. The equation we got was negative 8.67 meters per second. And the time, negative 0.06 meters. The equation tells us that for every second time, the marshmallow's position is increasing by negative 8.67 meters. Also, the y-intercept means that this is where the marshmallow was launched in relation to the ground. And for the velocity versus time graph, the graph here tells us the change in the speed of the marshmallow along the vertical axis. The equation we need was negative 9.8 meters per second squared plus 3.68 meters per second. The initial velocity, which is the y-intercept, tells us the starting speed. The slope is approximately negative 9.8 meters per second squared. This means that for every second time, the marshmallow's velocity is increasing by negative 9.8 meters per second. This infers that the slope is equal to the gravity, lowercase g constant. This also reveals that any projectile will have this constant downward acceleration. This is due to gravity pulling is making the marshmallow fall to Earth with a constant acceleration.
Okay, this is for our marshmallow project, and this is the Marshmallow force diagram and vector cell diagram. And for the vector cell diagram, when the marshmallow is launched, as you can see right here, the velocity decreases until it gets to its apex, which is right here. At the apex, the velocity is 0 meters per second. Then the first one changes direction. So when it changes direction, the velocity increases until it hits the person, coming to a stop. And then the distance between these, the marshmallow launcher and the person is 5 meters, which is equivalent to 15 feet. And then our force diagram, since we launched the marshmallow at a vertical angle, the force is equal above horizontal, and the weight must be down because gravity pulls an object down towards the Earth's center. And then the vector sum diagrams, last of all will be the force going up, weight going down, and the total force going to the right. And then this is just a label with different terms. And so since we launched our marshmallow at a vertical angle above the horizontal, Newton's first law would apply if there were to be no gravity. If there's no gravity, this would be the projectile's flight path. It would be a linear line because gravity is not affecting it. But if there is gravity, which is what we experience, then the shape of the graph would be parabolic. And we know that gravity acted on the marshmallow because right when we launched it at that angle, the velocity began to slowly decrease. And we know that once it reaches its apex, the velocity must be 0 meters per second. And then as it comes down back to Earth, the velocity begins to increase in the negative direction. So therefore, gravity is pulling it down. And Newton's third law states that for every action, there's an equal but opposite reaction. That can be illustrated when the marshmallow is hitting our target. If you see in the video, the marshmallow will actually bounce off our target, which indicates that the two forces are equal. So the force that's hitting the person is the same as the force that's opposing the marshmallow. That's why the marshmallow bounces off. Alright, thanks for watching everyone. I hope you enjoyed and learned at the same time.